Hello, jury members. We are Team Right Prayog, and we are here with the problem statement 25022, which is maximizing section throughput using AI-powered precise train traffic control. We already know that India's railway network is one of the largest and busiest in the world, serving millions of passengers and transporting vast quantities of freight daily. At the heart of this complex system lies a challenge that is both operational and computational, the train dispatching problem. This problem is also called as timetable rescheduling. It's not merely a matter of logistics. It is dynamic, large-scale combinatorial optimization challenge that demands intelligent and real-time decision making. We choose this train dispatching problem because it represents a critical bottleneck in modern railway operations. It's a problem that scales exponentially with each added train, junction, or disruption. The sheer number of possible routing and scheduling combinations makes it computationally infeasible to solve manually or through brute force methods. This is not just a theoretical concern. It's a real reality for train controllers who must resolve conflicts, reroute trains, and minimize delays under intense train pressure. Scalability is also a concern. As train traffic increases, human controllers cannot keep pace. So we need automation. Economic impact, like efficient rail operations boost productivity, reduce fuel costs, and improve public satisfaction. In face of disruptions, whether equipment failure or emergencies, an intelligent system can adapt and recover faster than human-led process.
Indian Railways today faces a big challenge, handling more and more trains and passengers every day. But the tracks, platforms, and junctions are very limited. Right now, decisions like which train should go first, where to cross, or where to halt, they are all dependent mostly on the section controllers. With growing congestion and real-time disruptions, this becomes very difficult. To solve this, we have developed a hybrid decision support system model that uses both operational research and artificial intelligence. Our systems dynamically optimizes train movements, ensuring safety, punctuality, and the best use of existing infrastructures. If there is any problem, like a delay or a breakdown, the system quickly replans and gives the best possible option. The controllers also get a clear and simple interface to see suggestions, track delays, and improve punctuality. In short, our solution makes railway operations faster, safer, and more efficient by giving controllers the right support at the right time. Thank you.
The Indian railways are always busy, and if something goes wrong, like a delay, the whole schedule can fall apart. We need a way to fix this mess. That's where our IDSS comes in, powered by an hybrid AI engine. What makes it hybrid? Like it's like two machines working together. First, the smart brain. AI learning through deep reinforcement learning. It tests solutions in a digital world and always finds the best move, even for tough delays. Second, the safety net. The math rules of operations research. These make sure every solution is safe, dependable, and follows the rules. Together, this hybrid power gives us speed, flexibility, and trust. So when things go wrong, we can quickly build a new schedule and give the human controller our best advice. The result: more trains on time, smoother service, and fewer delays for everyone.
Everyone, for the future of Indian Railways, intelligent management is more important than just speed. Right now, train systems worldwide use three main ideas. First one, ATOS. Like in Japan, these systems follow a fixed schedule exactly. They work well for simple traffic but can't handle real-time changes or problems easily. Next one is ERTMS. Like in Europe, this is the best safety rulebook. It makes sure that trains and tracks can talk safely, but it's not smart planning system itself. So next one is CTMS. Like in Germany, these use AI mainly for planning the schedule ahead of time. Our Indian railway network is special. We have super dense traffic and mixed traffic passengers and trains together. These whole systems are built for the real-time world complexity. That's why we are proposing a system IDSS. IDSS means Intelligent Decision Support System. So its main job is real-time fixing. It doesn't just follow a schedule. It creates the best new schedule the moment a problem happens. We give the best instant suggestions to our human controllers. This is called human in-loop support. The result is huge, phenomenal scalability, a big jump in capacity, and much better on-time performance for India's demanding network. Thank you.
Our Intelligent Decision Support System, or IDSS, is an absolute necessity for Indian Railways. Let's look at why it's the smart choice. The key advantages are huge. By optimizing every single train movement, we can unlock latent capacity on existing tracks. This means more trains can run without building expensive new lines. When a delay happens, our system performs large-scale reoptimization in minutes. This stops one small delay from becoming a national-wide crisis. Increased throughput and on-time performance lead directly to improved customer satisfaction and significant cost savings. But is it feasible? Absolutely, and yes, how. Our operational research model acts as a guaranteed rulebook. It ensures every AI session is perfectly safe and technically possible. Our human in the loop concept empowers controllers instead of replacing them. This preserves expertise and makes the system easy to adapt. We start with a targeted pilot project, managing risk and allowing the system to continuously learn before national deployment.
Coming to the prototype of our ARIS, a project designed to tackle the immense complexity of train traffic management on the Indian Railways network. We began this prototyping phase. Our team identified a fundamental challenge. The core of a system is a powerful hybrid optimization engine. But our biggest question was not about the complexity of the AI itself. Rather, the real hurdle was the one that required our attention the most. How do we actually show the IDSS is working? How do we show our ARIS system is working? The output of the system isn't some simple number or some pass fail result. It's complex, dynamic, and is constantly evolving train schedule for an entire network section. Simply showing a list of commands or a static timetable wouldn't prove anything. So the challenge was clear. We needed a way to visualize the impact of our system's decision over time and across the entire network. We had to create an environment where we could clearly demonstrate and quantify our improvements over the current manual system. So this is the version 1 of the simulator we have built. So this is the first version of our prototype. In this first version of our prototype, we have been able to build the whole simulator basic versions, like the whole fundamental thing. We have able to automate the whole simulation process. But what we lack is the connection of the signaling system to the graph. And coming to the second version, we are able to connect that too. Like for here, for this station, if I'm giving this to green, these two trains are starting over there. And if I again change it to red, this will automatically stop. Another thing we have implemented here is that we have introduced the station diagrams and that respect and you can see the respective status of the stations here.